I don't know if I guess we could start, and I can just say a few words real quick before I give the stage to Nicole. So I wanted to start by thanking Nicole and Matteo for this endeavor. It's been quite a few months since we've been planning this, and I think I'm really excited. I think everyone is as well. So thank you, really from the bottom of my heart. I think it's a really fantastic thing that we're doing here. And I also wanted to thank everyone for this enthusiasm. It's really great to see so many people interested in this topic. So what I propose we do. So I'll give the stage to Nicole, and she can run the lectures as she sees fit. So the course website will be constantly updated during this time. So let me post it on the chat window here. I'll also post it on YouTube in a second. So please refer to the website where we'll also post any kind of material and so on. And while during the lectures, I will monitor YouTube chat. So for those that are listening into YouTube, please know that there is like a 15 to 20-second delay. So there's always a small lag. Unfortunately, this is something related to Zoom. There was nothing we could do. But I'll be monitoring the YouTube channel, and you can then ask questions. I'll try to transmit them to Nicole and Matteo. Yeah, I guess that's it. I don't know if I have any other big announcements to make. The lectures are going to be recorded as well, and they will be posted on the website. So if you miss a lecture for any reason, you can watch it afterwards. Yeah, and I guess that's it. If I remember anything else that I forgot to say, I can just mention later on. But Nicole, I guess the stage is yours. Oh, by the way, sorry. I would also like to ask everyone to shut off your cameras and microphones during the talk. But if you ask questions, try to use the raise your hand feature. And also when you ask questions, if possible, try to open up your camera. I think that's nice to have a better kind of interaction, if that's possible. Okay. Cool. Thank you again, Nicole.
Thanks very much for the introduction. Thanks to everybody on Zoom and YouTube who are joining in. It, as Gabriel said, was great to hear of all the enthusiasm, and thanks a lot to Gabriel and Matteo and the University of Sao Paulo for coordinating and hosting and enabling this to happen. So a little information about me is I'm Nicole Younger Halpern. You can feel free to call me Nicole. I'm currently based at Harvard, but next year I'll be starting a group at the National Institute for Standards and Technology in the University of Maryland. So if you're going to be looking for a postdoc position or a PhD position and you'd be interested in doing quantum thermodynamics there, then please get in touch. Some deadlines are coming up. So our other lecturer will be Matteo Lastaglio, who is an excellent presenter and has accomplished some really important work in the field that we're going to be trading off on lecturing. And to reemphasize what Gabriel said, if anyone on Zoom has a question, then please raise a hand. I think that I won't necessarily be able to see questions in the chat unless a hand is raised. I'm going to do something a little bit different during this lecture. Sometimes at the end of a subsection, I will pause. I'll ask you to close your eyes for about 60 seconds and visualize what we just saw and heard. So this exercise has two purposes. First, staring at a screen for an hour and a half is good for nobody's health, including mine. So my visual system would probably protest. So this will refresh our eyes. And second, this exercise helps turn passive learning into active learning. If we just listen and just watch, we're engaging in passive learning. If we can recall what was happening and picture it in our mind's eyes, that will enable the memories to stick much better. With that, I'd like to start with a simple motivating story. If my iPad will let me write. There we go. So a simple story.
So Nicole, I'm sorry to interrupt, but I don't know if everyone's having the same problem, but I'm just seeing a kind of strange screen, not really the full resolution thingy. It's now kind of blurry. Oh, okay, now it's back for me.
Okay.
Okay, so
Let me know if that happens again.
for some reason it's zooming in, so sometimes it zooms in and becomes kind of blurry. Now it's zooming again.
Are you saying now it's blurry again?
Yeah, it's blurry again. So it wasn't, and now it is again. And now it's okay. So I don't know what happens, but yeah, so now it's okay. We can say perfectly.
Okay. This is a simple story about how information can be useful in a thermodynamic task. Our setup will be the favorite setup of physicists, a gas in a box. We have our box here. This is going to be a very, very, very simple gas, namely just one particle. And I'm going to have it be a classical particle to start with. It exchanges heat with a temperature T heat bath through the walls of the box. We're going to undertake this protocol. First, we slide a partition into the box's center. Then we measure whether the particle is on the left-hand side or the right-hand side. Since there are two possible outcomes, we receive one bit of information. In our story, the particle is on the right-hand side. Then we tie a rope to the partition and tie an Acme anvil to the rope. So, did anyone watch Looney Tunes? You know, those cartoons with Bugs Bunny and Daffy Duck? So, one of the Looney Tunes was a coyote who kept chasing this roadrunner, which is a certain type of bird. So the coyote keeps trying to catch the roadrunner so he can eat him. So sometimes the coyote takes this Acme anvil, which I will draw very, very badly, but I'll try. Something like this. A very heavy anvil. So he takes it up a mountain and he plans to drop it on the roadrunner when the roadrunner zips by below. Usually the anvil falls on the coyote instead. But either way, when I think of something that's heavy and that needs lifting, I think of an Acme anvil. So our engine is going to lift this anvil, but hopefully with less violence than the cartoon. After
Nicole,
that, yeah.
I'm sorry to interrupt. Some participants are asking if you could increase the resolution a little bit. I don't know if maybe using it in land screen would improve it. Because the way it is, it's a little bit hard to read.
Okay. I'm really unfamiliar with using an iPad, and so I'm afraid I don't know what to do to increase the resolution.
So if you could flip it to land screen, I think that already helps.
Okay.
Yeah.
Let me see. Can I put this away?
Yeah, I think there's this. Yeah. Okay. That's much better. Perfect. Yeah. Cool. That's perfect. Thank you.
How do I convince it to zoom out? Do you know how to get it to zoom out? I'm trying to pinch and pinch inward, but it's not working.
Yeah, I'm not sure it does, but for us that are watching, the resolution now is perfect. If you could leave.
That's great. The only problem is it's so big that I can't write anything.
Oh, okay.
For instance, I need this and this at the same time on the screen.
I see. Yeah, I'm not sure because you're using the Notes app, right?
Yeah.
I'm not so sure. Let me see if I can
Okay, I'll see. Try to move forward. I might be writing smaller afterward. And it might be a bit confusing because you can't see the picture and the writing at the same time, but we'll see what we can do.
Yeah, so now it pinched in.
Okay, unfortunately it's not pinching in on my screen. So it's just the same size.
Let me see.
But let's try to go forward for now. So we unfix the partition so that it can slide. And the particle is going to hit the partition. And it's going to punch the partition to the other side of the box. So this Acme anvil is going to rise because it's attached to the rope.
Yeah, Nicole, I'm really sorry to interrupt, but now for some reason we are only seeing half of the screen. I'm really sorry, but I don't know.
Okay, I think the problem is now. Can you see it?
Yeah, so now it went back.
Okay.
Okay. So let's try like this. If it works for you, it would work for us.
Okay. That wasn't supposed to happen. Let's see. The pleasures of trying out Zoom in a course for the first time. Here's our box again. And the rope was tied to the partition, so the Acme anvil has been lifted. We can start analyzing the problem. The anvil gains gravitational potential energy. Meaning we've done work on the weight. How much work can we perform? This work is of the pressure volume type. So we can write out this integral from the initial volume to the final volume. And we all know the ideal gas law. In our very idealized gas, the number of particles is 1. We can solve for the pressure in terms of the volume and substitute into our integral. The initial volume is half of the box. Let's say that the box has a volume V, and the final volume accessible is the volume of the whole box. Then we integrate. We then evaluate the limits and find that the maximum possible amount of work is Boltzmann's constant times the temperature of the bath times log 2. Where did this energy come from? Please go ahead and write your answers into the chat. Where did the energy come from? Entropy, that's definitely involved. Yes, the heat bath, exactly. I'm saying also as an answer, information. The information is very important. We'll get to that in just a moment. But just for the sake of satisfying the first law of thermodynamics, the law of conservation of energy, the energy that went into lifting the the anvil came from the heat bath. The heat is random energy. It's not coordinated. It's not doing anything useful. It's just energy of random motion. On the other hand, work is coordinated, useful energy that we use, for instance, to lift anvils and charge batteries and so on. So how did we turn heat into work? With the other answer in the chat, we used our bit of information. So at the end of the protocol, we have no idea where in the box the particle is. So we gave up our bit of information. In other words, we traded information for work. We can convert information plus heat into work. So later, we'll show that the arrow can also point in the opposite direction. But I wanted to provide at the outset of this lecture at least a taste of why it makes some sense to combine information theory with thermodynamics. This story comes from Leo Szilard, who was a great physicist of the 20th century. Okay, let's take that 1 minute break and close our eyes for about 60 seconds. You can, if you have video on for some reason, you can turn it off and visualize what we just saw and heard. Also, if you are going to ask any questions, this is a good time to come up with them. Hey, does anybody have any questions about Szilard's engine? Feel free to raise a hand if you do. One question is, could you please explain what happens to the particle's kinetic energy? The particle has kinetic energy that it uses to push the partition. That wasn't supposed to happen. There we go. It uses that to push the partition. And so as it pushes the partition, it does work on the Acme anvil. So the kinetic energy turns into gravitational potential energy, but more energy comes in to the particle from the bath. Okay, let's move on. Here's what I would like to cover in the rest of this lecture, but we'll see how far we can get in light of things like Zoom problems. We started off with Szilard's engine. Then I'm going to cover very quickly some background about thermodynamics and quantum information theory and their combination. So when I write QI, I mean quantum information or quantum information theoretic or something analogous. Then we're going to go back to Szilard's engine and analyze it in a new way. We're going to add quantumness, and we're going to look more closely at the relationship between information and energy. So this is Szilard's engine, take 2. Let me see, looked like someone raised a hand, but I'm having trouble seeing that. There we go. The purpose of the bath is to ensure the particle won't stop before it moves the wall. Yeah, basically the bath helps make sure that the particle is always, or let's think of it as an idealized gas, a very, very simple ideal gas. The particle is always at temperature T, so it always has enough kinetic energy to keep the wall moving. And assuming that the gas is at a constant temperature keeps our analysis simple. So we can always have that T in our integral when we use the ideal gas law. Okay, there are a lot of references about this field. These are just a few that I've found useful. In 2016, 2 reviews came out of specifically quantum information theoretic thermodynamics. These provide brief overviews of the field and recent developments. If you find a topic here that you want a whole mini review about, then you might find a chapter that came out in a recent book, which is Thermodynamics in the Quantum Regime. With a number of editors. This was published by Springer, but a number of the chapters appear on the archive for free. And for something totally different, which is more of a fun take on the field, there's an article I wrote this past spring in Scientific American, which is where my background comes from. This is usually behind a paywall, but Scientific American let us put it up on the course website for free.
So Nicole,
Yep.
there were a couple of questions. I guess the participants lowered their hands, but also on YouTube, there were 2 questions that I could maybe convey.
Okay.
So Thiago Santos asked, he has a question about information. So he's asking, as I understand, the information we have is in which part of the box the particle is in. Do we measure the particle, or do the slide gives us this?
We perform a measurement that tells us just which side of the box the particle is in.
Okay, fantastic. And then Tanmoy has a question. If the system were completely isolated and would not be able to exchange heat, would it be possible to get any workout?
I would expect that we could get some workout because the particle will still have some kinetic energy, but it might not move the wall as far.
Cool. Thank you.
I'm having some trouble finding the chat. Is it okay to use the ideal gas law since we have a single particle? Yeah, that is one of the objections. We could use a number of particles as our guess, and then just say instead, when we put the divider in, then we'll have some number on the left-hand side and some number on the right-hand side. And we hook up our anvil so that it is over this side that has more particles because they are going to push against the side that has fewer particles until reaching pressure equilibrium. It just makes the analysis a bit more complicated. That's a really interesting point. Do we need to make a measurement besides just putting the wall in? Won't the pressure on the wall reveal where the particle is? We need to make the measurement so that we know where to hook up the anvil, as in we put the anvil over the side where the particle is. Because if we put the anvil on the other side, then the particle would not raise the anvil. So that's how we use our 1 bit of information. But that is a really subtle point. Okay, let's provide a little bit of background and motivation for this field. Not everyone here is beginning at the same level of knowledge. There's quite a range. I'll begin with some basic material. Some people will know it very well. If you do, then please just bear with me. Let's start with thermodynamics. First of all, what is thermodynamics? Type your answers into the chat. Let's see if I can see the answers. There we go. The study of heat and work. Yeah, that's basically it. Or more generally, the study of energy. And the forms that the energy can take and the transformations between those types of forms. Sometimes I find that even when I work on a field, I don't always stop and think, just what exactly fundamentally is the field? What is the definition? So sometimes that's worth doing. What are the characteristics of thermodynamics? There are a few that sort of belong to the personality of thermodynamics. First, at least traditionally, thermodynamics focuses on large-scale properties. Such as temperature, pressure, and volume. In some cases, properties such as temperature can vary from point to point, but we don't even need to know what the system consists of. We don't even know whether it consists of particles. Suppose that you want to test whether some piece of physics is thermodynamics or statistical mechanics. In a very gross, coarse sense, thermodynamics, at least again, traditionally, involves no probabilities. Oops. No probabilities, no density operators, which are the quantum versions of probabilities. And again, a lot of thermodynamicists originally didn't even believe that particles existed. So we will use density operators and probabilities, but we'll still call our subject quantum thermodynamics because of characteristic 2. Thermodynamics is operational or agent-based. Thermodynamics was born in the Industrial Revolution. Thomas Savery had invented the steam engine in 1698. Thomas Newcomen built on it in 1712, and then James Watt improved it in 1776 so that it worked quite well. Now, people wanted to pump water out of mines, and then engines started powering factories. So people wondered, how efficiently can an engine perform work running between, say, 2 heat baths? Or more generally, how efficiently can an agent perform some operational task when given certain resources? Examples of thermodynamic tasks include performing work, preparing non-equilibrium states, and keeping time. In contrast, in statistical mechanics, we focus a lot more on calculating partition functions. And as alluded to in the chats, thermodynamics really spotlights heat and work, as well as efficiency. Some people might need a quick review of the concept of equilibrium. This is a state in which, first, all macroscopic properties remain about constant. And second, there are no net flows of anything into or out of the system. For example, suppose that we have a small system interacting with a big bath. Then the two can exchange things. Suppose that they exchange heat. Then we will ascribe a temperature T to the bath. I'll use beta to denote the inverse temperature, or KB is Boltzmann's constant. And the system and bath exchange heat until coming to thermal equilibrium. That is the sort of equilibrium here. If the system is classical, then suppose that nu of E dE gives the number of microstates with energy within dE of this number E. So the probability that the small system has an amount of energy very close to E is given by the canonical distribution, or the Gibbs distribution, which is going to keep showing up across these lectures. Here, this Z is the partition function. Again, this is the canonical or Gibbs distribution. If the system is quantum, then let's call H sub S the Hamiltonian of the system of interest, H sub B the Hamiltonian of the bath, and H int the interaction Hamiltonian that can move energy in between the two. We also assume that this is small in the sense of having some matrix norm that's much smaller than the norms of the other Hamiltonians. That wasn't supposed to happen. Here we go. Then our canonical ensemble turns into the canonical or Gibbs state. This rho B is a density operator, which people in this course are probably familiar with. It was mentioned in the prerequisites. For a quick review, it's a positive semi-definite linear operator. It also has unit trace because of the definition of the partition function. There are many quantities exchangeable by the system and the bath, such as particles and volume and electric charge. These lead to different types of equilibrium, such as chemical equilibrium, as well as different thermal states or thermal ensembles, such as the isothermal isobaric ensemble. Alternatively, we could have a closed isolated system, which someone asked about, I think, via YouTube when we were talking about Seelard's engine. The extensive variables remain constant. The energy, the particle number, the volume, and so on. So the system just thermalizes internally and particles spread out across it. So if the system is classical, then Let's denote by W the number of microstates with an amount of energy within a window of length dE about the number E, and same thing for particle number, basically. Then the equilibrium distribution is simply 1 over W. This is the microcanonical distribution. It too will come up later. If the system is quantum, then the system is confined to some subspace, H, of the total Hilbert space that's associated with a particular particle number and close together energies and so on. Now here the microcanonical state is the identity operator over the dimensionality of the Hilbert space. Some things that are not examples of equilibrium include a system that is between 2 baths at different temperatures. This has, say, T1, and this has T2 greater than T1. Then a net heat is going to flow through the system from the left-hand bath to the right-hand bath. Since there is a net flow, there's no equilibrium. Another example consists of us. We as organisms live very far from equilibrium. We are good at extracting ordered energy from our environments, namely food, and radiating lots of heat. Let's move on to the laws of thermodynamics. So before we completely move on, are there any questions about equilibrium, for example? Teacher is supposed to pause for a very long time before accepting that there are no questions. So there's going to be a really awkward silence for a little while. Okay, HS, HB, and H interaction are a Hamiltonian of the system of interest, a Hamiltonian of the bath, and the interaction Hamiltonian that enables the two to exchange things. If the dimensionality of the Hilbert space is infinite, yeah, I guess I usually don't think about that case very much. But also, the identity operator is going to be, oh, just a minute, is going to be also defined on the whole space. So still this quantum state should be normalized. And in the case, so I imagine that you're thinking about infinite dimensional state spaces because of continuous systems rather than discrete systems such as qubits. So in this case, we define the microcanonical ensemble in terms of a Dirac delta function. So the Dirac delta function is going to be focused at some energy. So that'll, yeah, give us a particular energy. Oh, lots of questions. Does the equilibrium depend on what H interaction is? If we're deriving the state, the thermal state, like the Gibbs state here, then an assumption that tends to go into the derivation is that the interaction Hamiltonian is very, very small and can actually be neglected. If the interaction Hamiltonian is not small, then we might not get a state that looks like this. And it's possible that Matteo will talk about that later on. In the traditional sense, how would we classify heat engines and refrigerators? Are they examples of non-equilibrium case? So a heat engine will act between two baths. They're at different temperatures. Each of the baths is at equilibrium. There is a net flow through the system, like in our first example, or our first not example of an equilibrium system. So if this is the engine, then we might wish to say yes, since there's a net flow of heat through it, it's not at equilibrium. In this description of equilibrium, the classical idea of unstable equilibrium makes sense because it seems that every equilibrium will be stable since system plus bath are evolving toward it. It sounds like maybe you're thinking about fixed points in condensed matter. In the case of equilibrium, well, there are some ways we can talk about stability. For instance, you can, as we'll talk about shortly, find that depending on what situation you are in, there's some free energy or another equivalent function that is relevant to the situation and tells you about how the system might behave. It's used in a principle similar to the principle of least action in classical mechanics. And the principle of least action gets us to points where the derivative vanishes. And similarly, when we're dealing with a free energy, the free energy tends to minimize at equal, the free energy does minimize at equilibrium points.
So Nicole, Pedro Correa is also asking a question in YouTube. He asks, how do we define equilibrium time in closed quantum scenario?
So if you want to measure time, then you need a system that's out of equilibrium and that dissipates. If the system is in equilibrium, it's possible that Matteo will talk about this because he has done some work on it in the quantum context. If you have a system that's in equilibrium, then the state is time invariant. So you can evolve it with a Hamiltonian, and suppose that you take your canonical states, which is here. Suppose that you take your states, you evolve it in time with its own Hamiltonian. You'll put a unitary on one side, you'll put U dagger on the other side, and U is defined in terms of H sub S. So the unitary will commute to the other side, and these will cancel to the identity. So you'll be left with the same state. So this thermal state does not change in time. So it can't act as a clock, it can't keep time, it doesn't register the flow of time. So you need a non-equilibrium system to register time. Lots of great questions. Let's for now move on to the laws of thermodynamics. So it's a very basic question. Just remind us, how many laws of thermodynamics are there? Just type the number into the chat. Okay, most of the answers are 4. Excellent. Yes, naturally they begin at number 0. So the people who formulated the 0th law believed that it was so important that it should come first. But by that time, laws 1 through 3 had already been formulated and were already known by their numbers. So these people gave this law index number 0. Let's see if my pencil wants to work. Yes, great. So anyone who remembers the topic of the 0th law, type it into the chat, just the main subject. Temperature, entropy, temperature. Okay, most people are saying temperature. Yes, so temperature is definitely involved. Let me give a slightly different way of framing the subject and focus on a thermometer. The 0th law states that if system A is in thermal equilibrium with system B, and B is in thermal equilibrium with system C, then A is in thermal equilibrium with C. This is a law of transitivity. So suppose that we know the temperature of C. Then we can infer system A's temperature by using B as a thermometer. Then what is the subject of the first law? Type it into the chat again. Yes, conservation of energy, exactly. Let's define, or let's denote by U, the system of interest, internal energy. Let's call W the work performed on the system. Again, this is useful energy. It might be harnessed to push a car up a hill or charge a battery or something similar. Let's denote by Q the heat absorbed by the system. Again, this is useless energy because it's random. Then the first law states that any change in the internal energy comes from the sum of the work in and the heat in. What is the second law about? Again, just type the subject into the chat. Delta S greater than 0, entropy, yes. It's about entropy, and it's sometimes synopsized in the phrase, you can't break even. There are many formulations of the second law. I'll review one of them. This states, as someone mentioned, that the entropy of every closed isolated system increases monotonically. Or delta S is at least 0. There is a concept of thermodynamic entropy. Suppose that our system is closed and isolated and at equilibrium, and it occupies one of W possible microstates. Then the thermodynamic entropy is Boltzmann's constant times the log of the thermodynamic entropy, and that is on Ludwig Boltzmann's tombstone. So we'll see some other entropies later. There are a number of great quotes about the second law that have been spoken over the past few centuries, so I'll read one of them. This is from Sir Arthur Eddington. He was the astronomer whose observations of a solar eclipse provided some of the first experimental evidence for the theory of general relativity. So he is the reason why Albert Einstein became a household name. So he wrote in 1915 a book called The Nature of the Physical World. He said, the law that entropy always increases holds, I think, the supreme position among the laws of nature. So if someone points out to you that your pet theory of the universe is in disagreement with Maxwell's equations, then so much the worse for Maxwell's equations. If it is found to be contradicted by observation, well, these experimentalists do bungle things sometimes. But if your theory is found to be against the second law of thermodynamics, I can give you no hope. There is nothing for it but to collapse in deepest humiliation. After that, the third law seems like an afterthought. But what is the subject of the first law? Let's type it into the chat again. Absolute zero temperature. Yes, great. Again, there are multiple statements of the third law. I'll review one. It says that a system's entropy approaches a constant that is independent of the pressure and the external magnetic field and so on, as its temperature approaches absolute zero. So entropy is a measure of the number of states available to the system. At zero temperature, the system can only occupy its ground states, or if there's a degeneracy, ground states. Those are the laws of thermodynamics, but alas, all is not well in thermodynamics. Thermodynamics was developed in the 1800s, a long time ago, for big classical systems like steam engines, mostly at equilibrium. Some topics are missing. Small systems, quantum systems, and far from equilibrium systems. Some of these have been addressed in various ways over the years. Also, Szilard's engine showed that thermodynamics is closely intertwined with information processing. So we need, as a community, to re-envision the 19th century theory of thermodynamics for the 21st century. And so we need a toolkit for updating thermodynamics, which will lead us to quantum information theory. But let's take another minute-long break, visualize what we just saw and what we heard, and think of any questions. Hey, does anybody have questions about thermodynamic background? Because of decoherence and energy fluctuations, how can a quantum system be truly in equilibrium? Yes, equilibrium is an idealized concept. And in fact, thermodynamics is defined in terms of a very idealized concept, the thermodynamic limits, in which the number of particles and the volume approach infinity. We're doing physics, so yes, it's going to be idealized. Equilibrium can be well approximated in a number of systems. A system tends to have some relaxation timescales. So if you wait for a time that's much larger than the relaxation timescale, then you might expect that the system is well approximating equilibrium. Why did you make the distinction between small and quantum systems? Some small systems are classical. And we will possibly see some of those in the next section. In a Leonard Susskind lecture on statistical mechanics, he mentioned the -1 law, which states that information is never lost. Is this true? That might be a designation created by Lenny. Let's just say the negative first law of thermodynamics is not standard. I hadn't heard of it before. I wouldn't be surprised if Lenny put it into his lectures. It is very widely accepted, and it comes in part from a very quantum information theoretic way of thinking. There's actually a debate about whether information is never lost. It looks to me personally like information is not lost, but there are some people who think otherwise. what are the failures of thermodynamics? Some of the missing pieces are the ones that I mentioned here: small systems, quantum systems, and far from equilibrium systems. Although thermodynamics has definitely expanded by now to accommodate, for example, a whole subfield called far from equilibrium thermodynamics. Can dE be replaced by a finite delta E? Yeah, you could integrate dE over a region delta E. Is the thermodynamics of small classical systems not well studied? If so, what are the problems? We're going to talk about some of those during the course of the lectures. Yeah, I wouldn't be surprised if someone like Charlie Bennett supported the -1 law. I'm saying it's not standard. And there are some people, it's not in textbooks, it's not in most presentations of the laws of thermodynamics, which go from 0 to 3. Now, it's possible that 50 years in the future, textbooks will include a -1 law of thermodynamics. We just have to see how the theory as a whole evolves. And again, I personally like the idea. Since it's just not standard, I wasn't going to present it. And yeah, there are still some people who think otherwise.
So Nicole, there are also a couple of questions from YouTube.
Okay.
Frank is asking, on Ziller's engine, won't the measurement disturb the system? And also maybe related, can the particle...
maybe we could take them one at a time so I can remember the first question.
Sorry, apologies. So the first question
no
is,
worries.
Ziller's engine, will the measurement disturb the system?
Yeah, we're going to talk about that actually when we get to Szilard's engine part 2. That's very relevant for quantum systems.
Okay. And then the related question would be if the particle can tunnel between the left-hand side and the right-hand side.
Well, we were assuming that the particle is classical. You can also change the setup so that the particle is quantum, and we'll do that eventually. Then you could have a barrier that is thin enough that there's a significant chance of tunneling. You could also make the assumption that, well, there's a time scale associated with tunneling. So you could assume that things happen over a time scale such that the particle is very unlikely to tunnel to the other side. Or you could take tunneling into account when you do your analysis. So there are both options.
Cool. Then there are 2 more questions. So Kispiri is asking, mainly what I'm interested in is what do we hope to achieve by constructing a theory of thermodynamics extended to the quantum regime? Like, how would I explain that to friends or family?
Well, how about we go through the rest of the lecture and then come back to that question if it's still around.
Cool. And then finally, Franklin is asking, in this context of information loss, what would motivate not believing in information conservation in thermodynamics?
A very fun topic to do some reading on if you have time after the lecture is the black hole information paradox. That's what's led to this controversy.
Oh, thank you.
The black hole information paradox and also some recent developments in it. There's something called the AMPS firewall paradox. Right, thanks for all the questions. And let's move on to quantum information theory. This is the study of how we can use quantum phenomena to process information in ways impossible for just classical systems. So by process information, I mean solve computational problems, communicate information, secure information, and store information. And by quantum phenomena, I mean a host of things. So entanglement, measurement disturbance, particle number statistics, if we have many quantum particles, and quite a bit more. So how efficiently can we perform information processing tasks? So the answer is usually a function of an entropy. Entropies are functions defined on probability distributions, or quantum states. They quantify uncertainty about the outcome of a measurement of the quantum state or the value of a variable distributed according to the probability distribution. Lots of entropic functions exist. We'll see a few over the course of this course. I'll, at the moment, introduce two to start with. One is the Shannon entropy. So I am in the Boston area, and how the weather will be on any given day in the Boston area is a very, very random variable. We're interested in a discrete random variable, which I'll call X. So the weather might be sunny, it might be cloudy, it might be rainy. So these are possible values of the random variable. Let's say that there are D possible values. So the weather has a probability of P1 of being sunny, a probability P2 of being rainy, and so on. So these probabilities form a probability distribution. We can motivate the definition of the entropy, the Shannon entropy, as follows. I'm not going to give the complete motivation because that would take a little long, and this is a very short class. But suppose that today turns out to be sunny. Unfortunately, that is not true in the Boston area. But for the sake of this lecture, suppose that today turns out to be sunny. So the amount of information you learn if the weather turns out to be sunny, or how surprised you are, is called the surprisal. And it's defined as the negative of the log of the corresponding probability. The log is usually base 2 because we measure information in bits, but when we use the entropy in thermodynamics, we will often change base to base E. So if P equals 1, then you are not surprised because there was a 100% chance of sun. So you can't be surprised at all. You learn no information. And indeed, the negative log of 1 is 0. If P equals 0, there's a 0% chance of sun, and yet somehow it's sunny, then you're infinitely surprised because the sun should have been impossible. And indeed, the limit gives us infinity. Suppose that you check the weather every day, then your average surprisal equals the Shannon entropy. Which we can now define. So the Shannon entropy of a probability distribution big P is the negative sum over the probabilities Pj log Pj. So we took the negative log Pj and averaged it over Pj. It's useful to look at extreme values. For example, the minimum value. This is realized if the outcome is totally determined. But if the probability distribution has a 1 with just a bunch of zeros after it, or some permutation of what I've written. In this case, the Shannon entropy equals 0 because we define 0 log 0 as 0. So in this case, you can predict the weather with certainty every time. You quit physics, you become a weathercaster, and you make a lot of money. The maximum value of the Shannon entropy is attained if the probability distribution is uniform. Suppose that there are, again, d possible values of our random variable. Then the probability distribution will consist of a bunch of instances of 1 over d. In this case, the Shannon entropy equals log d. If you have a classical closed isolated system at equilibrium, then the number of microstates accessible to that system is d. Then log d is the thermodynamic entropy to within Boltzmann's constant. The second type of entropy that we will cover in this very brief review is the von Neumann entropy. This time, our setup involves some quantum system associated with the density operator rho. And for the sake of simplicity and relevance to the following material, we'll focus on a discrete Hilbert space of dimensionality d. Then we will define the von Neumann entropy of rho as negative of the trace of rho log rho. This reduces to the Shannon entropy of the spectrum of the state. We can write the states as an eigenvalue decomposition. So suppose that Pj denotes the jth eigenvalue, and the state has eigenstates j. Then Pj is the probability that, if you measure the state's eigenbasis, you obtain outcome j. That's the set of Pj's forms the spectrum. The von Neumann entropy of the states equals the Shannon entropy of the spectrum. Again, there are some extreme values that we should take a quick look at. The minimum value is attained if the system is in a pure state. We can write our density operator as one outer product. then the von Neumann entropy vanishes, as you can check by writing out the spectrum and calculating its Shannon entropy, or just plugging into the definition. The maximum value is attained if the system is in a maximally mixed state. It has the form of the identity operator over the dimensionality of the Hilbert space. Then the von Neumann entropy maximizes at the log of the dimensionality of the Hilbert space. We said that entropies quantify the optimal efficiencies with which we can perform information processing tasks. So let's see an example of that. See an example. The example of data compression. Suppose that I want to send a message to Matteo. We agree beforehand on the possible letters, some pure states x1, x2, and so on until xd. So Matteo knows the probability that I'll send x1, the probability that I'll send x2, and so on. So he knows this probability distribution. To Matteo, my state has the form of a mixed state in which the possible letters are weighted by their probabilities. Now suppose that I send some large number n of letters or copies of the state. I send, in Matteo's view, this tensor product. Our task, should we choose to accept it, is to compress the whole message into the least possible number of qubits. So the qubit is the basic unit of quantum information. Some people here will be very familiar with qubits. Some people here might not be familiar with qubits. If you're not familiar with it, the concept, I recommend looking it up after the lecture. It's the basic unit of quantum information. It's a quantum two-level system exemplified by the electron spin. It's represented by a point on the Bloch sphere. If you're unfamiliar with the Bloch sphere, I recommend looking that up for homework. And a popular basis for the qubit Hilbert space is 0, 1. So how many qubits do we need? The answer is given to us by Schumacher's theorem. Which states that the minimum number of qubits that I need per copy of the quantum state in the limit as the number of copies approaches infinity is the von Neumann entropy of that state, which quantifies Matteo's average uncertainty about which letter I'm sending. So in conclusion, an entropy quantifies the optimal efficiency with which we can perform an information processing task, namely data compression. There's a very similar scenario in thermodynamics, namely isothermal, or at a constant temperature, work extraction. Maybe it would have been, yeah, let's say compression instead. Suppose that we have, again, our favorite system, a gas in a box. Suppose that This gas has many classical particles. They're anywhere in the box. And again, our gas exchanges heat through the walls of the box with a bath at a fixed temperature T. So that's heat. Then we want to compress the gas quasi-statically, very slowly, so the gas is always in thermal equilibrium with the bath. We need to calculate the work done on the bath, on the gas by the piston that we are using to compress the gas. How do we solve this problem in thermodynamics? We identify the relevant free energy. Since only heat is exchanged by the system in the bath, the relevant free energy is the Helmholtz free energy. I will often denote free energy or shorten free energy to Fe. This has the form of the internal energy, I used to denote that by U, minus the temperature times the entropy. Here S is the thermodynamic entropy. And the minimum amount of work required is the change in the free energy. The final free energy minus the initial free energy. So here, an entropy helps quantify the average efficiency with which we can perform a thermodynamic task, namely isothermal compression. So in both information theory and thermodynamics, entropies help quantify the optimal efficiencies with which we can perform operational tasks. So entropy forms a kissing point between information theory and thermodynamics. And quantum information theory is a useful toolkit, for example, for analyzing quantum computers, but it is just this mathematical and conceptual toolkit that we can apply all across science to gain new lenses on other fields. We analyze quantum systems in terms of how much information they can carry and transmit. The fields include condensed matter, high energy physics, including black hole physics. A lot of quantum information theory is being used in the black hole information paradox that we were just talking about, atomic, molecular, and optical physics, chemistry, biophysics, and so on. Let's take another minute-long break and visualize what we just heard and saw. Any questions about quantum information theory? I have a question about quantum information and thermalization. According to quantum mechanics, the universe evolves unitarily, so entropy is constant. According to the second law, entropy can only increase. What gives? Yeah, it seems like there's tension between those 2 points. So the whole universe does evolve unitarily, and the whole universe's system, the whole universe's states cannot experience an entropy increase if we believe that the whole universe evolves unitarily, as far as we know it does. But suppose that you look at a subsystem. It will increasingly, in certain quantum cases, entangle with its environment. So that system will experience an entropy increase. You can think of that system as a system of interest and everything else in the universe as an effective bath. So your system of interest eventually will thermalize. And this is exactly the points of a lot of experiments that have been done in quantum many-body systems recently. The whole system is closed and isolated, but if you look at one system or one subsystem, say a few qubits in a whole chain of qubits, then you'll see that their entropy increases. When I think non-unitary evolutions in quantum mechanics, I think decoherence. Is it accurate to think of thermalization as decoherence? If so, is it accurate to say that entanglement causes thermalization? Thermalization in quantum theory involves more stages and has more properties than thermalization in classical systems. And decoherence is a part of the thermalization process in quantum systems, and it does involve entanglement. So do closed quantum systems violate the second law? I think that might be covered in the answer to the last question. Can we prevent thermalization in open quantum systems? If you work very hard, then you can. For example, if you measure the system constantly, then approximately. In Schumacher's theorem, if n tends to infinity, then system tends to classical. In this case, we think about a whole bunch of independent qubits, and the qubits are independent, but we will eventually average over them. So since they are independent, they are not interacting systems, and the interactions would make the system act somewhat classical. So I see there are more questions. Unfortunately, we're getting towards the end of the lecture. There's a lot of material that I'm going to hold off on for the next lecture, but I did want to get to a homework problem because hopefully you'll find it kind of fun and we can talk about it at the start of the next lecture. So sorry about not being able to get to all the questions. Now we can think about combining quantum information and thermodynamics. So on the one hand, we can use quantum information theory to modernize thermodynamics so that it can be applied to, for example, experiments happening today and quantum computers. But on the other hand, we can use thermodynamics to understand better what distinguishes quantum from classical physics. Oh, and there was another question on the chat about going more slowly because of a lack of quantum information background. I'm really sorry about that. This is a really, really broad course. There are loads of people with lots of different types of background. So I'm trying to pitch to a certain set of grad students for which this course was basically supposed to be designed. So I'm sorry if it's too fast for some people and too slow for other people. Hopefully some background reading could help. If it's background about quantum information theory that you need, then I strongly suggest Nielsen and Schwang's textbook. So we know that we can use quantum phenomena to process information in ways impossible with classical systems. For instance, quantum computers can solve some computational problems much more quickly than classical counterparts. And we know from Szilard's engine that information processing is very much intertwined with thermodynamics. So we might expect to be able to use quantum phenomena to perform thermodynamic tasks, such as work extraction, in ways impossible for just classical systems. So that's how thermodynamics can help us understand what separates quantum physics from classical. Before the lecture ends entirely, I did want to introduce a homework problem. This is not working as I expected. Oh well, there will be a stray 6 on the board. Let's go back to Szilard's engine. We learned that you can use information to turn heat into work. Let's think about a slightly different scenario. Well, this was going to be section 4 in, or subsection 4 in this section, but let's make it section 1. So consider the following setup. We have a tiny ratchet, which is going to be drawn very, very badly, but it's a little wheel with teeth sticking out of it. It has a spring mechanism attached to it. Winding the ratchets, let me think about, okay, in this direction, let's say. So winding the ratchets costs work because you have to push against the spring, which gets stored as the spring's potential energy. Then unwinding releases potential energy from the spring. There's also a pawl. This is a little tooth that catches on a tooth of the ratchet. So if you can wind the ratchet so that the pawl falls on the next tooth, then the pawl will prevent the ratchet from unwinding and will ensure that the work that you did to wind the ratchet is now stored for good in the spring. There's also a thermal bath at temperature T. And our little system here is at thermal equilibrium with the bath. The story involves some action, but I'm going to claim the following. So the bath, having thermal energy, is going to kick the ratchet. If the bath kicks in the unwinding direction, then the pawl prevents the ratchet from unwinding, so that can't happen. But if the bath kicks the ratchet in the winding direction, enough so that the next tooth comes to rest on the pawl, then the ratchet captures that information, that energy from the bath, and stores it as potential energy. So the ratchet appears to take heat from the heat bath and store it as a spring potential. So the potential to perform work. We need to figure out, for homework, how do the ratchet and pawl not violate the second law of thermodynamics. So think about the question, write up your answers. Don't search online or in books or papers. We'll discuss the problem at the beginning of the next lecture. Does anybody have questions about the homework problem?
Yeah, so once we do the homework, we have to send it, or how does it work? I mean,
you'll just have the homework for yourself. We're not going to check it. We're going to discuss it at the beginning of the next lecture, but it's just for your own sake.
okay, yeah, got it.
Any other questions about the homework? When does the pawl stop the winding? So if you wind in this direction, then I'm not great at drawing, so this won't look very good, but you make this tooth, or let's see, did I draw it in the wrong direction? I think this works. Here, let me erase this. Then you take this tooth and move it up here to right here. Then the pawl, this here, is now going to fall between two new teeth. So that is how, if you wind the ratchet past a certain point, then the pawl will come to be between two new teeth. So it'll prevent any unwinding, and it causes the spring to store the work that was required to wind the ratchet. And if you input more work, then you can turn the ratchet further and store more work as potential energy of the spring.
Nicole, there's also a question from YouTube.
Okay.
So Kiz is asking, is the pawl being pushed by the heat bath as well?
That's something that you can think about during homework, as you do the homework, and let me know what you think tomorrow. But I guess a simpler, more direct answer is this whole system here, if I can write, there we go. This whole system, no, I still can't write. There we go. This whole system is in thermal equilibrium with the heat bath. If there are no more questions, then thanks for all the questions during the lecture. We'll come back tomorrow and talk about the homework question and then variations on Szilard's engine and a lot more. Are the compression energy negative K dx and heat bath energy KBT comparable? I suggest that you think about the different cases during the homework and write out what happens in each case.
Okay, cool. So I guess that's it. So thank you so much, Nicole, and thank you, everyone. We'll then reconvene again tomorrow, same time.
Great, thanks everybody.
Awesome.